by 900, you got a factor of safety of about 4. Okay, so this is how it works. So let's go back and take a complete look. We started out, I'm going to shrink it back a little bit so that you can see everything. There, that's much better. So we started out, of course it's kind of tiny, but I wanted to keep it, let's make it a little bit larger, okay. So, started out with this, we had the motor and housing, so we had to figure out what was happening to the load. So we went and looked it up and we found out that we are going to look at the worst case. The worst case is when the motor is going to stall. So we looked up and we said, okay, what's the stalling torque of the motor? It's about 12 Newton meters. By the way, for typical motors, if you want to figure out what the load is, this is what you do. You just assume the worst case scenario. You're going to stall the motor, look up the stalling torque. And that'll give you a pretty good idea of what to start, okay? So 12 Newton meters, you're going to create that by applying a force at about 100 millimeters from the disc, from the center of the disc. So that's 120 newtons. And then you know that the relationship between normal force and shear force is mu times normal force equal to shear. So we look up mu and we found out it was 0.6. So we found the load. And there's a lot of uncertainty in this. You can see that, right? So please, if you get slightly different answers, don't panic. There is no magic answer to all of this. This is very approximate. When I said that the factor of safety is 4, it may be, it's typically more than 4. What we are saying is that the factor of safety is at least 4. In the same way, what we are saying is that the friction force is at most 120 newtons. Not more than that. The normal force is at most 200 newtons. Can you see that? We have found the upper bound of these things. Okay. Then we did a material fatigue analysis. We found SUT, SY, SE prime, SF, the usual stuff. Then we found out surface finish, size factor, K, load factor. If it is combined load, we always put load factor equal to 1 because we will fix it when we compute the stresses. Temperature factor was 1. So we found out the SE was 306. Once you get that, you can plot our safe and unsafe regions for the material. So this region is safe, that region is unsafe. That region is finite life, that region is unsafe. If you are here, it will last for a few cycles, not many. If you are here, it will last forever. Okay. So then we came to the major part of the analysis. You have to do 3 pieces. You have to look at it from the end on first to calculate the torque. And typically this will be mean torque. It's very rare to come across torque fluctuations. Okay, so this is mean. So this will always go into the mean load column. Then we look at the top view or side view, and in either of them you can see the 200 Newton normal force. Okay, in the top view we calculated the normal force 200 newtons. That will also be typically constant. For a shaft type situation, normal force will typically be constant. It's very rare for that to cycle. Okay, the main cycling is going to be bending moment, so pay attention to that. And then in the top view we computed the bending moment. Whenever you look at the top view and you compute the bending moment, it will be along the y direction. It will be rotating around the axis of the page. Okay, side view you do the same thing. You compute the bending moment, it's called mz, and then you compute the total is square root of my squared plus mz squared. Okay, mx is called torque, so that's separately counted. Okay, so then we found out we can do our list. This to see the list, I'm going to blow up this thing so that you can see it properly. There. So what we did was we calculated alternating and mean, bending, torsion, axial, bending, torsion, axial, and we filled it out. 209 alternating bending moment, no alternating torque, no alternating axial load, mean bending moment none, mean torsion 12,000, mean axial load 2,000, minus 200. So from that we computed MC over I. For a circular geometry, C is 8, I is pi d fourth over 64, R is d over 2, J is pi d fourth over 32. You can compute all of that and you can get the stresses. About 52 megapascals, 14 megapascals, axial is 1 Newton, 1 megapascal. We don't care about axial loads usually. We don't care about axial and shear. I told you, right? When it is torque and bending moment dominated, axial and shear loads will be very small. So what happens is, then we compute KT there, and then we compute the what is that, the knot sensitivity, and hence you calculate KF. Once you computed KF, you can get the corrected stress, 64, 15.7, 1.2. Who cares about the 1.2? Then you can do the sigma alternative. This is equation 635 and 636 in your text. I think so. Let's make sure. Sorry, let me make sure, okay? Because I want to make sure that I'm telling you the right equations. There, 655 and 656. You can see that in your text, and those are important equations, okay? Because we'll be using them to compute always the equivalent loads, okay? So you compute that, and you found out that your equivalent mean load is 65. Equivalent mean load, that's not right. Equivalent mean load is 27. Equivalent alternating load is 65. And so you can compute, you can go back and plot it on your figure. It's there. That point you are very safe. How safe you are is computed by looking at the factor of safety, 1 over sigma A over sigma E plus sigma M over sigma UT, which is 4.1. 4 factor of safety. Got the thing, right? So it is going to last forever, and with a factor of safety of 4 at that location. The inside the gearbox may break. That part will not break. The joint where this thing goes into the housing, that part is not going to break. Something else may break. So I want you to understand, you have to look at each joint and figure out. Okay, with that we are done.